or good evening. Yeah, good morning and good evening. Thanks for waking up so early in this wet, rainy Saturday morning, and to joining me for what could be a very boring topic for many of us. And I will try my best to make this useful for each one of you. So this talk should take about 20 to 25 minutes, and hopefully at the end, you will be able to somewhat relate to HPC, understand what it does, how it does, and some of the challenges from engineering perspective. You could use this for your general knowledge perspective or to map out the skills needed if you are interested in pursuing a career in HPC or decide to totally stay away from it. Hopefully not. So high performance computing, or HPC in short, what comes to your mind when you think about HPC? Something super high tech, some nerdy people wasting a lot of money, sometimes government money, to do some fun stuff, or used in some weird or niche areas to solve something that is totally detached from all of us. What if I say HPC influences many things around us? That HPC is a crucial factor in making some of the things that we all come across daily. Even things such as, or as simple as soda cans. Well, thank you, Deepthi, for the nice introduction. Yes, I'm Anil Vatalai. I've been a MEA member for ever since I moved to Houston. I've been practicing HPC for the last 14 years in the capacity of software developer, architect, manager, and so on. Currently, I hold the position of VP, responsible for software and digital solutions at CGG. You can use the QR code to connect with me in LinkedIn. CGG, the company that I work with, is a technology company with its headquarters in south of Paris. They focus on geoscience and high-performance computing. And what you see here on the slide is a HPC and AI-generated image of me. Of course, one of the many things HPC can do. Now, back to soda cans. We don't consider soda cans or beverage cans as a high-tech product. We may not fully appreciate the impact soda cans have on our environment either. Yes, soda cans are low-tech, but they are high stakes. Let's see why. People use them constantly. Globally, we use about 6,700 of them per second. That's 180 billion aluminum cans every year, which means a slightest design flaw wastes tons of aluminum and millions of dollars. It takes more energy to mine and produce aluminum than any other material. That's interesting. The energy it takes to make 4 soda cans is equivalent to filling one of these cans with gasoline. And 2% of world's energy use is spent on producing aluminum. That's a lot. Designing a can may seem a very simple task. In reality, beverage cans are one of the most highly engineered products manufactured today. Tiny changes in product geometry can result in profound performance improvements and savings. Identifying the best possible design requires consideration of 26 different parameters through 67 million finite element computations for the math geeks in you. So if you are using typical FE analyzer methods for this task, the design cycle could take 150 years. Of course, that's too long for us to afford. So they use HPC to do it faster. I'm sure we have people in this audience who works on pharmaceuticals or oil and gas industry. So drug discovery and deep water oil well, what do they have in common? They both are expensive processes. The cost to develop a new drug averages $2 billion. It takes from 12 to 15 years and has a less than 10% success rate. And people who are in the oil and gas, Drilling a rig in Gulf of Mexico cost about 500,000 US dollars per day. And if you hit a dry well, that costs millions of dollars. Decision-making in both cases involves analyzing huge volumes of data with complex scientific algorithms and simulations. They both rely on efficient high-performance computing. I take Biosimilitics as an example. It's one of our clients. This is a startup company in Ireland focusing on innovative methods for studying molecular crystallization. Molecular crystallization, those who do not know, is a step in the process of finding a new drug, where the right combination of the chemical compounds to be used in a drug will be found. It's a process that traditionally done in the lab, and they have to experiment with 50 or 60 different combinations before narrowing down to one. So regardless to say, it's a time-consuming and expensive process. These days, it's possible to simulate this process using computer algorithms without having to physically experiment with each compound mixture. So Biosimilitics has their proprietary technique that uses advanced software models to study molecular crystallization process. And this reduces the costly lab-based method, and reduce the cycle time. So HPC enables companies like Biosimilitics to reduce the cycle time for each experiments from several months to hours. So what we call in our side, turbocharging the drug discovery using HPC. Now, Biosimilitics, we may not be able to relate so much to their story, but we should be able to the COVID vaccine. You remember 2019, 2020, millions of people were infected and hundreds of thousands of people lost their lives to COVID. Finding a vaccine was a race against time. A vaccine can't come soon enough, but history suggests that it takes many years before a workable vaccine is widely available. The average time to develop a new vaccine is more than 10 years. And even the fastest developed vaccine for Ebola took 5 years. Finally, pharmaceutical companies were able to deliver COVID vaccine in record time, which really changed the face of COVID pandemic and allowed us to resume our life. So HPC had a huge role here. Through the consortium, the COVID-19 HPC consortium, some of the largest supercomputers and tech firms came together to donate unprecedented amount of HPC capacity into this problem. The target was to accelerate the discovery by 100 times or even more. And you can read from this IBM blog. Even if every person in the world is doing 1 million calculation per second, that will be about 8 petaflops of compute power. Flops is floating point operations, is a measure used in HPC world for representing the compute power. The COVID-19 HPC consortium was offering about 50 times more than that for vaccine discovery. For sure, HPC contributed to the speedy introduction of COVID vaccine. I guess enough talking about soda cans and COVID vaccine. So the point here is HPC is everywhere and it touches many things around us. It plays a crucial role in optimizing how we live, how we use the resources. So it is relevant for all of us. So what is HPC? As you can see here, HPC or high performance computing generally refers to aggregating computing resources together in order to perform more computing operations at once. So in some ways, it's a capability rather than a thing. Imagine what you can do with a CPU or a CPU core. Now, what happens if you put many of such cores together? You can do much more things faster. That's what happens in HPC. They put many of such cores, tens and even hundreds of thousands of them together. By doing so, HPC can process data and perform complex calculations accurately at high speeds. A computer system, just to give a perspective, a computer system that we have at home with, let's say, a 3 gig or 3 gigahertz processor performs around 3 billion calculations per second, and that's fast. But some of the HPC systems can perform quadrillions of data calculations per second, 1 million times faster. It's a different scale. What you see in the picture here is the world's largest supercomputer. It's named Frontier, installed in the National Lab in Tennessee. This is the world's first exascale supercomputer and the fastest as of 2024, like beginning of this year, leading the top 500 list. Top 500 is a list that tracks all the largest and the fastest supercomputers in the world. Floating point operations, or flops, is a way, as I mentioned earlier, is a way to describe the compute capacity in HPC. This supercomputer can perform 1.6 exaflops of compute per second. So to put that capacity into perspective, to match what an exaflop computer can do in just 1 second, you have to perform one calculation every second for 31.5 billion years. This performance comes at the cost of added complexity, which is one of the most interesting computer science challenges in working with HPC. Consider a simple real-world problem like putting 1,000 index cards into alphabetical order. This problem could take a long time for one person to do, but it's not too complicated to do. One person simply sits down and sorts the cards using the knowledge he or she has in their head. No need to talk to or coordinate with anyone else. What do you do if you want to make this faster? You recruit more people to do this process. But even adding a single new person dramatically adds to the complexity. The two people now must work together in some ways. Even if they start each by sorting their stack individually without speaking to one another, they're still having to cooperate at the end to sort the cards or two stacks into one. And there are many different ways to do even this seemingly easy thing to be done. The exact same problem exists in cluster computing. The problem of getting the processors to work together on a single problem is largely a software challenge, but the software needs the hardware in order to work. Two processors cannot talk to or speak to each other unless they are both connected to the same network. You will need to make sure you have the right processor for the compute task that you're running, the right amount of memory, disk, and the right cluster interconnect, and so on. So with that note, let me introduce some of the basic pieces that makes all of this work in HPC, both hardware, and I will start with hardware, followed by the software. So again, to start with the compute, which is most of us familiar with. We all are familiar with the term of a CPU or a core. So a core is the smallest unit of compute when we refer to compute chips. A CPU chip can have multiple cores, more than one. The latest AMD Genoa has about 96 cores in one chip. Now, a blade can have one or more of these CPUs and all the necessary hardware to make use of the CPU, including memory and network capability. And when you move to a cluster, that's how we install all this compute power in an HPC data center. A cluster will usually be a rack of blades, hundreds of them usually with network switches, power supply, all the cabling, etc. In data centers, most of these components will have the redundancy like power, networking, and so on, the redundancy for obvious reasons. Now, there are three major components in HPC hardware: the compute, racks of them; storage, again, racks of them; and then the interconnect or the network to put all these pieces together. Usually, a compute operation starts with reading the data from the storage, which usually disk-based for performance, followed by performing a series of compute operations that's on the compute side, usually in parallel, and eventually send the data back to the storage. That's a typical cycle of operation in HPC. Now, let's dig a little bit more into compute. So Intel and AMD, the familiar names, lead the compute world for CPUs. Intel used to be the leader, and it is very well challenged by AMD these days. Then, of course, there are accelerators. Using GPUs for general purpose computing was one of the major breakthrough in HPC world a decade ago. So GPUs are basically graphics cards that we used to have always for driving our monitor or the graphics in the monitor. But about 10 years ago or 10, 15 years ago, we start to use that for general purpose compute. And they are a lot faster. NVIDIA is the leader here. And you can see that from NVIDIA's, people who follow the stocks, you can see where it is, this company. AMD is a challenger, and Intel is trying to compete, not quite there for the GPU world. GPUs came in the forefront of large-scale computing through the rise of Bitcoin mining, and it is accelerated several folds through AI and more recently, generative AI. NVIDIA Hopper cards H100s is the runaway leader in this revolution. And H100s and the demand for that through generative AI is one of the main reasons of the race in, or the astronomical race in the NVIDIA's value these days. And for compute, ARM is getting more and more attention these days. So for example, NVIDIA is using them for compute. And so is the FPGA or field programmable gate arrays. Those are specific purposed compute chips. The latest trend in the chips is that people combine these days CPU and GPU in a single chip with directly shareable memory. Again, NVIDIA is the leader with their upcoming Grace Hopper cards. Now, if you move to storage, you can look at this from a very different perspective. Obviously, storage is for storing the data for longer term usage. The medium used to store is one way to look at the storage. Tapes, the magnetic tapes, the old-time ones are still used for cold storage. Spinning disk for cheaper but live storage, and solid state or flash disk, which is what we get in the latest laptop these days. The solid state disks are used for faster storage to provide the type of access speeds expected by the faster and faster compute node. In HPC, usually there will be storage that is local to each of compute nodes, and there is a concept of shared file systems. It can be parallel file systems such as NFS, or very likely something like a Lustre or GPFS, etc. And then there are object storage. Those who are familiar with the cloud technologies, Amazon S3 will be a familiar term. Ceph is one of the open source object storage, very popular in the HPC world. And in the world of network and interconnects, most of the latest and fastest HPC systems will use some sort of InfiniBand connections. And while Ethernet-based networks are still popular and cost-effective option in the data centers. While hardware is extremely important, it's not all of the HPC. There are several layers of software above the hardware that makes all of these work together. HPC is generally dominated by Linux-based operating systems. HPC software is usually written in C or C++, Python, and so on. And some of them for scientific representation, they use Fortran. These codes will be compiled for the specific CPU or GPU platforms. So there will be compilers and libraries for the hardware platform or the targeted hardware platform. Cluster software includes managing swaths of compute, storage, and network resources. These days, more and more converged software-defined deployments are prominent. So cloud platforms such as OpenStack or OpenShift are used. They also provide virtualization, which includes several other players such as Proxmox, VMware, and Nutanix. The hardware is closely monitored for availability, performance, and utilization. and it is usually automated through software again. Cluster deployment is managed through tools like Ansible and Puppet, because it is just not possible for people to manually and independently or individually manage all these. To manage workloads at a very large scale, schedulers such as Slurm is widely used. In our data center, like the company that I work with, we manage about more than a million HPC work, what we call the jobs in a single day. So we just cannot manage this efficiently without a scheduler. So we use tools like Slurm. Then you are in the application space where there are specific scientific application packages. Some of them are not so specific, but general purpose, but some of them are very custom targeted applications. And the framework such as MPI is used to parallelize the computation. So through this stack, this HPC stack, you can not only understand the different pieces of HPC, you can somewhat map out the different skill sets and job opportunities if you're interested in a career, and hope it helps. The people with system administration, a deep understanding about networking, security, operating systems, hardware, they are of high demand in the HPC world. So as the people with mathematical and software background. So I started with placing HPC in the daily life, then looked at what is HPC and how it works through some of the components of HPC. Before I conclude, I like to touch upon one of the major challenges for HPC today and going forward, which is specifically relevant for all of us with the significant increase in AI-based workload and the changes in our climate that we are witnessing. So in this slide, you can see on the very left, a picture of NVIDIA H100 chip, the most highly sought after chip in the world these days. In the middle, you can see the skyline of Phoenix, the US city in Arizona with a population of 1.6 million. And on the right-hand side, you can see the map of Georgia. It's a European country with a population of 3.6 million. Do you know what all these three have in common? They consume same amount of power. H100 cards consume 700 watts of power at peak. At 61% annual utilization, it is equivalent to the power consumption of an average American household occupant. And NVIDIA expects to sell 1.5 to 2 millions of them in 2024. That will be placing them just below Houston and just above Phoenix on residential power consumption, and comparable to the consumption of some of the European countries such as Georgia. Think about it. Yes, electric cars are important, and it is very important to make sure the data centers are operated in an environmentally responsible way. Cooling these cards in the data centers are major engineering challenge in HPC. So I'll just touch upon some of the techniques that we use to cool these extremely hot commodities in the market. And the air cooling is one of the popular one, which is pretty old technology, but very widely used. Direct to chip cooling, it's specifically targeting the most heated components in the blade. And then on the right, you can see immersion cooling, usually immerse the entire blades into some material such as mineral oil or synthetic oil for extremely effective cooling. These are some of the cooling technologies that we use. On that note, I like to thank each of you for listening, and I really hope it was worthwhile. Once again, feel free to contact me through LinkedIn using this QR code. Thank you so much. Thank you, Deepthi. Back to you.
Okay, thank you, Anil. It was a wonderful session, and I learned a lot. I think everyone learned a lot from this HPC world. And so if any of you having questions, you can start asking question, unmute and start asking question, or you can post the question in the chat. I didn't see any question in the chat. So if anybody is having questions, please unmute and ask. Yeah, we got one question, Anil. It's from I'm not sure. Okay, what kinds of job opportunities are available within the HPC?
Yeah. So that if you follow the stack of HPC, the different layers that I put in one of the slide, you can see there are a number of hardware related topics there. And it doesn't need to be totally, people who work on putting pieces of hardware together, but a very solid understanding about computer architecture would be very helpful to get started with HPC. In HPC, you can work on the application programming area, which is software development or scientific topics like mathematics, physics, and so on, or even some biomedical background. So if you are interested in that field, using computer science as a medium, you can get into HPC in the application development or software optimization area. Then there is a field of system development, again, where you work very closely with computers. So a deep understanding about how computers work, how, for example, disks are used to store the data. This is something that we will study in computer engineering if you are interested in that. And then there is quite a bit of software involvement again there. So generally, studying computer science is one of the a good first step to get into HPC area. And the job opportunities could vary from system engineers to infrastructure programmers to algorithm developers or application developers.
Okay, thank you, Anil. Okay, another question. What is the status of quantum computing in HPC?
Yeah, so there are two questions, one
Yeah,
after that,
related.
heard about quantum computing. So
Yeah.
quantum computing is still, I don't want to say it's heavily used. It's still a field of investigation and research. So basically in compute terminology, we talk and we work in binary bits. So you have the way you represent data is either ones or zeros. In quantum computing, using specific materials, you are able to have more than two states. So it's not really deterministic, right? So using that, you are able to do much more computing. That's the idea of quantum computing, and it's a field that is still developing. I mean, if you go to conferences and so on, you will hear a lot about quantum computing, which is the case for several years now, but it is hard to see somebody is really like making a good use of that. And for quantum computing, excuse me, the relevance or correlation definitely is there because high performance computing, as I mentioned, it's a way to parallelize or putting together many computers to work. So HPC is really relevant for using quantum computing whenever it is ready for general purpose use. And I guess HPC is now confined only to supercomputing. No, that's not true. Supercomputing, again, usually the term supercomputer is used when extremely large. So I was showing the Frontier as an example. And many of the national labs, whether it is in US or Japan or China, even Singapore, they have supercomputers, which is usually managed by national laboratories funded by government. And the scientific research agencies share them to do research work. But it is not required for supercomputing or supercomputer for HPC to work. Many of the HPC sites, like for example, the company that I work with, CGG, we have 500 petaflops. That's half an exaflops of single precision floating point compute power. And we don't call ourselves as supercomputers. It's distributed, grid-based. And it's not a uniform set of machines, if you like. the equipments are brought in at different periods of time. So it's not necessary for supercomputing or supercomputers to work with HPC. How many companies are in the business of doing HPC? How old is this industry? So the company that I work with, we are in the business for, or I can't say we are, but this company has been in the business for more than 90 years. And we have been using HPC in the last 30 to 40 years. And we don't call them HPC necessarily in the past. It's like cluster computing. And then nowadays you can see even cloud companies like, for example, Amazon, Azure, Microsoft Azure, and Google. They all have HPC offering. And many of the scientific computing companies, like commercial companies, for example, if I look at our compute capacity, we probably be 7 or 8 in the world in compute power for the published numbers. But the commercial companies, we don't publish numbers. So there will be several who operates in this industry. I would say I would rather look at it from the field. So if you look at, for example, satellite mapping, you look at weather forecasting, you look at medical research, oil and gas, energy, even media production. All of them uses HPC for their day-to-day activities. And with AI, you can imagine going forward, the demand is going to be extremely increased. So there would be much more number of players who comes into HPC industry. And I heard there is a lot of investment going on, even using or coming up with a lot more data centers in an extremely, the areas that we probably wouldn't have thought about in the past. For obvious reasons, like cooling is really important. So cold countries would have very much interest in having data centers. Is big data analytics using MapReduce, Hadoop, etc. considered part of HPC? So look at it from a different perspective. HPC is a capability to provide compute platform. And you can use HPC for many different type of application. So big data analytics like MapReduce and Hadoop, they are techniques to do specific type of processing, which you will or you can do on top of HPC. In fact, the Hadoop, MapReduce, and so on, and MPI, they are just different flavors of how to parallelize your workflows, which you need compute anyway, and that's what HPC is providing. How is HPC used for deep neural networks and reinforcement learning? But again, this is the same thing. You have deep neural networks and reinforcement learning that comes as part of the AI or generative AI. And they are applications that requires compute power, large scale of compute power, and that's what HPC is providing. Usually, the modeling and inference requires GPUs and large number of them with extremely high memory, as you can imagine, with trillions of parameters in each of their model, which if you want to provide that much of memory and compute, you need HPC to do that. And so, yeah, generative AI and AI in general, they use HPC to do that. That question is interesting. My journey. So I started as a software developer. So I have a degree in information systems. And I started as a software developer with CGG. And I have been working as a software developer, mainly on the application space. Then over the period of time, I'm deeply involved with our company's HPC activity. So my journey has been through the same company. Started as a software developer, application space, and then moved on to other areas of digitalization and HPC implementations and so on. I hope that helps, Shahjahan. I don't know if you have more details. You can talk to me directly if you have. The HPC use in crypto mining and blockchain, yeah, back to the same topic. These are applications which require, so for example, crypto mining and blockchains, they use GPUs. And they have a requirement to, depends on the size, they have a requirement to put together large volumes of compute power, memory power together. And that's what HPC does for them. So Joseph, I think I need to make sure that you understand the difference between HPC as a capability to provide large scale compute and the applications that you can run on top of them. So it can be for mining, crypto mining, it can be for AI, it can be for drug discovery, it can be for geoscience, data processing, it can be for weather forecasting. All these are different type of applications that runs on top of HPC. The difference would be you don't necessarily use the same type of GPUs or CPUs that you use for crypto mining for, let's say, weather forecasting. You probably need a different type of hardware, and you probably need a different type of interconnect to, depending on the amount of data that you need to move between the CPU chips and the GPU chips and the memories of each of them and your final storage. So all these configurations can be different, but underlying technology or that capability we call HPC. Hope that helps, Joseph.
Yeah, I have a couple of questions, Anil.
Okay.
Okay, so the way you have mentioned, and also the demand, it's expecting it's very high for this coming years. So are you thinking it's going to shift the technology to something else, or will it continue for like the 3 to 5 years like this?
There is a sustainability challenge here. We just cannot assume that we can continue to consume just like, I mean, without paying too much attention. I mean, we have seen that, that kind of thinking or shift in the way we do. For example, if you look at the way we have been using plastic, right? I mean, in the beginning, nobody cared about how we use, things like plastic. But then people start to be aware of the importance of environment and the impact it has on environment. So in the HPC world, we have the same problem. So you look at the industry these days, or generally in the world, the energy consumption by data centers are coming into a very prominent space, right? And the way the industry approaches is in two directions. One is try to use the energy efficiently. So I mentioned the case of H100, 700 watts, like the average power used by a household in America. But if you compare H100 with its previous generation, it is able to do more than like 6 or 7 times activities than its predecessor. So it does use more compute power. It does use more energy, but it is able to perform much more things than what it used to be in the past. So there is an optimization in the hardware sector that is happening. Then to cool these GPUs and to reduce the power, there is a lot of effort in optimizing that area. And then in UK especially, it's quite interesting the way they think about how to, for example, reuse the heat generated in HPC for other purposes. So in cold countries, they use this heat to, for example, provide heat for the houses. So somehow like reuse the energy for innovative purposes. Again, these are not commercially or most widely used, but this is one direction in which the industry is approaching this. On the other hand, and that's really where I think answering to Ditya's question earlier, the role of software developers comes in, or the research comes in. you can write a program to perform a specific task. And the first time you write, it may not be very optimized. So the impact of that would be it runs. I mean, usually we think about efficiency as the time it takes to get things done. But in HPC world, the time is one factor, but the energy used to do a particular task is another one, right? So the optimization can be done not just by speed, by energy utilization. So there is a huge role for software developers, the application developers to optimize their algorithms, optimize their applications so they will run more efficiently, faster with lesser energy. So in going forward, yes, we will continue to see the evolvement of generative AI, trillions of parameters, several folds bigger than what our brain cells have, right? That is not going to slow down. But those algorithms will become more and more efficient going forward in reducing their demand in using energy. So overall, it can't just continue this way. Like, for example, we start to have limitations on adding more compute power in our data centers because these giants are, it's just not possible for us to manage the power requirement. I think we are probably one of the highest power users in the Houston area, right? So we just cannot go ahead with without any change. So there will be optimization on the way, the hardware, the power usage, the cooling, the reuse of energy, and then there will be optimizations of these applications to support that.
Okay, thank you. And I have one more question, so related to the energy source. So are you depending like the solar because it's needed huge amount of energy, right? So
Yeah.
are you guys using the renewable energy type of sources like a solar or something else?
Definitely. I mean, it's not a question that I can answer for HPC as an industry. So each of them will be using, in fact, much more exotic ways to seek power and cooling, right? I don't know if you follow the news. Microsoft had data centers under the sea, seawater. So that's one way for them to reduce the need for cooling. And I think Iceland and those areas are very popular for data center construction because the natural cooling effect that they have. And most of the companies like our power usage, I mean, we don't specifically generate power through solar or something ourselves, but the contracts that we have for energy usually are 100% renewable type of energy. So we rely on the energy industry to help us on that, but we pay for it.
Okay. Thank you, Anil. I think one more question came in the chat.
Is GPU the basic processor for high performance computing? I won't call it the basic processor, but again, CPU and accelerators. So it can be GPU, it can be FPGA, and so on. So they are accelerated technologies. So usually the difference is that, and as I mentioned, GPUs are, in the past, they are only used for performing the graphics operations for our monitors, right? So they are good at a specific thing. Like, for example, ray tracing is what they do best. So GPUs are not general purpose chip. They cannot do everything. I mean, CPUs are more general purpose chips. So CPU can generally do a lot of things. GPUs are more specific. GPU will be doing specific tasks, but extremely fast. And there will be large number of cores in a GPU's chips because it is very specific. So that's why you cannot use GPU for everything that we do on, say, for example, a basic sorting. It might not be very interesting to do sorting of data. It might not be too much interesting in GPU to do. But if, let's say, there is a ray tracing or AI algorithms, the GPUs are specifically targeted for certain application or certain activities. So they do that well. And the difference is that because they only need to cater for specific application, they can put in far more number of cores into the same chip. So the capability, when you look at floating point operations, would be extremely high on a GPU rather than a CPU. So which is why the if you see the trend of compute power, GPUs are dominating. It's mainly because of this rather than they are the basic processor. And I don't know if we can say something as a basic processor. And if anything, I would still say CPUs is the base. They even a GPU card, when we put that together into a unit of compute for us to operate, there will be a CPU chip in it. And that CPU chip is the one who usually do the networking activities, the data access. All this will be done through the CPU. And then and usually if you look at a software application that is using GPU, it will be using CPU plus GPU to work. And there will be memory transfer between the CPU memory and the GPU memory, along the application, which is why the new Grace Hopper from NVIDIA is interesting because CPU and GPU are in the same chip and they share the same memory. So it doesn't have to go out. So it will be an extremely fast situation.
Okay, thank you, Anil. Any more questions?
Yeah, Naveen here. I have one question, Anil. I think you touched upon this in different parts today. It's about the applications, the trend that you see from a few years ago to right now. What kind of changes that you can see in the trend of on the applications of HPC? For example, you touched upon the traditional requirements like oil and gas or weather or wherever. But nowadays, what are the changes that you see in terms of the applications and the type of companies and requirements coming in?
Yeah, so if I look at CGG as an example, we have been only focusing on geoscience in the past. And we realized that geoscience is an area where we need to use petabytes of data, and we need to process them in order to provide accurate images of the Earth. So that's one of the areas where we used HPC. So we did not intend to be in the business of HPC in the past. We developed the HPC capacity in order to serve our internal needs. And I'm pretty sure there would be several companies who does the same thing. And over the 30, 40 years, we realized that we have been doing this extremely well for our internal use, and we can use this for external other activities as well. And then now CGG HPC is a business by itself. And we look at companies that are engineering. So people who are using, say, for example, computational fluid dynamics for studying the motion of whatever material. We look at biomedical or biochemistry for some of the examples that I mentioned. And we also spoke with many of the people who are in the weather forecasting, weather modeling, and so on, because they're kind of like related to geoscience data activities, right? So those are what we call I don't know, you can call the typical or old type of applications, but those were the traditional use cases, what we thought we use HPC for. Then, of course, drug discovery coming under the biomedical. And then the things have started to change since, again, the use of GPUs. And one of them that really, really made use of that is Bitcoins. And people who made money out of Bitcoin a lot, I think they have GPUs to thank for and HPC to thank for.
Yes, right.
And then
Absolutely.
the next game changer came in AI, where we start to map out the AI, and that requires extremely large. They are really, really resource hungry. So that's the latest sort of like a change in application space. And in fact, today we are having an extremely hard time to get the chips that we want, because all these companies who are into generative AI, they are just consuming everything that they can produce. So you can see the H100s, everything that NVIDIA is planning to produce that are already consumed. So
Okay, thank you.
Okay. So do you have data centers like in every region, Anil, to meet the needs, or like is it everything managing from US?
No, we do have data centers. So Houston, the place that I work, that's the biggest that we have. In Houston, we have about 375 petaflops of compute capacity. We have data center in London, south of London. We have data center in Singapore. We have data center, a small one in south of Paris. Yeah, these days, these are the places we have data centers.
Okay, thank you.
Because, in many of these industries, they have a data residency requirement. Especially, if you're in oil and gas, if you're in medical, if you are in environmental, they don't allow data to be moved from one country to other in
Like
many
GDPR,
cases.
right?
GDPR is part of it, but even
Yeah.
without GDPR, that comes into personal space. But let's say geophysical data is considered, trade secrets, or um, um, the governments have restrictions. Some of the governments, like for example, Indonesia wouldn't allow you to move the data. Saudi Arabia, they wouldn't allow you to move the data. So there are restrictions. And I think even Brazil has some restrictions in that sense.
Anil, this is Lakshmi. I have a question as well. So, how is your HPC comparable to Azure or AWS HPC platforms?
Comparable in what
Or
sense?
different, like how do you sustain when you have HPC platforms provided by these giant companies like Microsoft and Amazon? So, how do you?
Yeah.
Yeah.
So it's a trend that we see. I mean, these companies see that the opportunity in HPC investment. Their biggest attraction is the companies that work with HPC usually will have a large volumes of data, especially they are in energy or environmental or even bio, in those areas. So the way they see is that they invest in HPC, and then they bring companies, usually through corporate marketing and so on, into the HPC side for Azure or AWS. It works in many cases, not necessarily efficient in all cases, because HPC is not, I mean, I think you probably got a glimpse of that. It's not like installing a general purpose activity. HPC can be specific to the application that you're running. The HPC configuration that you may need for biomedics is not the same as what you need for AI. And it is not the same that you need for, say, geophysics or energy processing. So there is a non-standard requirement, a collection of different type of configuration that you need for HPC, depending on the application and in the domain. So the approach of cloud companies was more like volume-based business. You have more people doing the same thing, they can have the economy of scale, and they will be able to make money out of that. That doesn't necessarily work with HPC. So the companies that, the energy companies such as BP, Exxon, Chevron, or Total, who moved big time to cloud for their HPC, they start to have the second thoughts because they have huge volumes of data and you can store them. To enter HPC, it's like a Hotel California. You can come in, but you cannot get out easily, right? So they will start to charge you for getting the data out and so on and so on. So over the period of time, the economic aspects are much different. So to give you a comparison, in some cases, like for example, storage, some of our clients who are using Azure or AWS, they pay probably like 10 times more than what we do for our internal storage. So, but at the same time, these companies have deep pockets like Azure, AWS, and so on. So they will be able to sustain and remove many of the competition. lot of people who does not necessarily have very specific requirements or very demanding needs for HPC, they will very well be happy with cloud providers through their HPC. But for those who are having specific requirements, there would still be a need for using customized or their own on-prem HPC. And I think the trend these days would be more about a hybrid compute. Even for us, in some cases, it makes sense for us to use cloud computing. Hope that helps, Lakshmi.
Yeah, definitely. Thank you. So your niche experience and customization capability and economical aspect is all what makes you different.
Yeah, Biosimilitics, the client that I mentioned, is a case study. They were with AWS. They were with AWS for a couple of years, and they came to us. Their applications are running probably like 5 to 10 times faster and cost effective with us than AWS.
Thank you. That helps.
How does HPC change with the cloud migration with new technologies, Nutanix, integrated computing, storage, and networking software? HPC changes, I think cloud migration, I guess I answered that with Lakshmi's question. But virtualization is a big thing because it is not just possible for us to manage bare metal computing or resources manually. So the virtualization has a huge role in that area. The Nutanix and so on, they do provide the ability to virtualize almost everything. And that's actually a big trend in the data centers, what we call the hyper-converged data centers. Who are our competitors? So we don't compete like I'm talking about CGG, which is not what I was thinking about when I started this talk. But for CGG, Amazon or the public cloud providers are not our competitors. As I mentioned, we are offering what we call outcome as a service rather than CPU pay-per-use infrastructure as a service or platform as a service or whatnot. So basically, we work with companies who are normally in a scale-up mode. So they were startups, they were successful, and they want to scale. So we work with them and we get their applications and we have a collaboration to optimize the application and HPC together with them and to get the best outcome for them. So this is one of the unique capability that we launched last year. We don't know if anybody is competing in that specific field, but there are similar players like, for example, Down Under from Australia comes to mind, and people like that who could be in the area of application hosting. So we are not purely a cloud hosting or HPC hosting company. We are a company who work with the clients to optimize the application to provide the best possible outcome. So we are still finding the competitors in that space. But in HPC in general, there are specific competitors or players, several of them.
Okay, thank you, Anil. I think we are good. So if you have other questions, please reach out to Anil and he can answer those questions, or we can actually plan for another session this year. And this was a wonderful session, Anil. You actually took us to the HPC world, and you actually taught us a lot about the HPC, where it can be used, all kind of things, and clarifying all the questions. And thank you so much for your time, Anil, and thank you so much everyone who joined and asked the questions and supported this event. Okay, thank you so much. And if you have other questions, please reach out to Anil. We can plan
thanks
another
everyone. I wasn't actually expecting so many questions. 25 minutes talk and 35 minutes question. That's really good. I think people were listening there.
Exactly. It was an interesting topic, Anil. Yeah.
Thank you. Thank you so much.
Okay, thank you so much. Thank you, everyone. Have a great rest of the day. Thank you. Bye-bye.